This is tutorial 8 question 2. In here we are almost doing the same problem as in question 1. We are given a matrix A and we are told that lambda equals to minus 2 is an eigenvalue and we want to find the eigenvector corresponding to this eigenvalue. Let's now introduce some terminology. The word eigenspace is a common terminology used. We'll say lambda eigenspace of A in here, meaning that lambda is the eigenvalue. We are saying that we are finding the set of eigenvectors associated with this corresponding lambda, and we write it as E lambda, the eigenspace corresponding to this lambda. So basically we are trying to find V belonging to Rn such that AV equals to the lambda V or the V's, okay, the space. Now it might surprise you, you will think that each eigenvalue will only have one eigenvector, but that's not true. Sometimes one eigenvalue can have multiple eigenvectors. So for example, if you enter this matrix, and you can use MATLAB to evaluate this matrix, you will get lambda equals to 344. So this is a repeated eigenvalue, and for each of these eigenvalue, in this particular case, we can find the corresponding eigenvectors. The eigenspace of lambda equals to 4 is not one vector. We can find two independent vector, and the answer is here. Of course, in MATLAB, if you put it up, you will see the scaled version of this. So I will show you what MATLAB does now. Over here, this is the matrix A that I have added, and then I use P for the eigenvectors, D for the eigenvalues. EIG is the eigendecomposition by MATLAB. We get P equals to these three columns are the eigenvectors, and 344 showing the eigenvalues. So in short, we have just basically discussed that you must be careful that there might be more than one eigenvector corresponding to one eigenvalue. Alright, now back to the question. We want to find E lambda equals to minus 2, the vectors, the eigenvector space of lambda equals to 2. So let's write what we mean. It is set of independent eigenvectors with eigenvalue equals to minus 2. That's the definition of eigenspace E lambda equals to minus 2. So to solve for that, what we are actually asked to find is A minus lambda I x equals to 0. We are asking to solve for x, that is x not equals to the 0 factor. And to do that, we begin by stating what is A. Let's write A first. Lambda equals to minus 2. Lambda I is equals to this 3 by 3 matrix here. And then we are going to now write A minus lambda I. What we get is equals to 314, 0 minus 1 minus 13 minus 1, 0, 3. This matrix you should check. It is definitely singular. The rank is 2. To solve for the eigenvectors, again as before, we write this in the augmented matrix and we are solving for x by performing Gaussian elimination. I'll not do the details here. What we finally get is 1, 0, 0, 0 minus 1, 0, minus 1 third, 1 third, 0. And then now we are going to solve for x. So we want to solve for x equals to x1, x2, and x3. We know we identify the pivots first. And we know that x3 is the free variable. We'll write the equations now. We'll have x1 minus 1 third x3 is equals to 0 minus x2 plus 1 third x3 equals to 0. Therefore, x1 is equals to 1 third x3, x2 equals to 1 third x3 as well. Therefore, this is equals to, we make x3 the free variable, and we can put 1 third here for the first equation, for the first entry, and the other one is also 1 third for the second entry for x2, and the last one is 1. What we have found is that this is any scale version because this is the free variable and this is the corresponding eigenvector associated with lambda equals to -2, associated with lambda equals to -2. Now, because this is any, so what we can choose is some simpler number. We let x3 equals to 3, therefore we are ending up with 1, 1, 3. Okay, so e minus 2 equals to span of this vector. That's it. Thank you.